Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
She started working on smart fabrics. Well, she did a lot of things at MIT, actually. She did the first high-tech fashion show, wearable devices. She worked with Todd Mockover on the brain opera. She built circuits and used them in innovative ways, but it was clear from our first conversation that smart objects and smart materials and smart clothing was just a really exciting scheme. So here, 6 years later, she's living in Seattle. She started her company, International Fashion Machines. She's a visiting scientist at UW. And this stuff is now not just speculative, it's going great guns, although, as Maggie's going to tell us, there are lots of challenges to that. So
yeah.
I'll let her explain.
I actually left the challenges out, but I'll fill them in at the end. As Turner said, I'm Maggie Orth, and today I'm going to talk about the art and technology of electronic textiles. I believe electronic textiles are at the intersection of design, technology, and material making things with your hands from physical materials. I have a small company right here in Seattle. I was going to say in Cambridge, Massachusetts. I just moved here. So right here in Seattle, and we develop electronic and interactive textiles for art, architecture, interior design, fashion, and the military. I actually have 2 Phase 1 DARPA grants, which is great, and medical industries. I'm the CEO, Research and Design Principal at the company. And as Turner said, I have a PhD from the MIT Media Lab, an MS from the MIT Center for Advanced Visual Studies. So I really have a hardcore artistic training, and I have a BFA from the Rhode Island School of Design, a really strong design and traditional arts training originally. So today I'm just going to I'll give you an overview of my talk. I'm going to quickly go over my early work in physical computing and new interfaces because I think it's relevant, sets the stage to what I do now. I'm going to talk about the technology of electronic textiles, my artistic motivations, electronic textile displays, and electronic textile sensors. The big question that I'd like you to keep in mind while I do my talk today, because sometimes while I'm looking at the details of my work, the big question may not be specifically addressed, is how can material making and computation come together? As a person that has always loved to make things, that has always been a challenge for me. How can I have the experience, the visceral experience of making things, and also experiment with computation? Other things that are in my mind when I'm working today are how can we imagine an interactive painting, and how would we make one? Today, artists, all kinds of artists, are taking their paintings, taking pictures of them and putting them in Flash and animating them. And I think my work presents an alternative way to think about what an interactive painting would be, where it's really a making experience, a physical making experience where software and computation, paint mixing, and basically canvas and textile mixing, pattern, issues of perception all come together when you're making your piece. And what are the alternatives to video, rate, and emissive displays? And what does that mean if we really want to work as technologists with technology that isn't the fastest, the brightest, the best, and what can we do with it that presents an alternative? And what does it mean to add time to traditionally static media, like a painting or a textile design? I think I skipped a slide here. I'm just going to go back. I'm a little stalled. So I do want to go over while I'm waiting for my computer to decide to go back for me, I do want to go over what electronic textiles are. So electronic textiles are basically linear circuits, and textiles that can function as linear circuits and linear electronic devices. They're nothing complicated, but they have to be carefully made, and the materials and hold on, I'm a little bit stalled here. Sorry about that. My computer seems to. Let me see if I can get this to respond. There we go. They can be woven, sewn, embroidered, or knitted. So basically they're made with traditional electronic textile processes, though the future for them is really in non-wovens. And there's a lot of reasons for that. And they're made from conductive or optical yarns and fibers. And there's a variety of conductive and optical yarns and fibers available to use out there. Stainless steel yarns, plated yarns. There's just a whole range of materials. But they're basically, all those materials are basically resistive elements. There's nothing in a nonlinear range. There's definitely research in transistors and research in more complicated yarn structures. But those things are ways away from actually being able to be put into a textile for various reasons. And because of that, an electronic textile is always coupled with a traditional electronics. So an electronic textile is basically an extension of a piece of electronics, a board. And what we can make with electronic textiles is still compelling. We can make sensors, we can make keypads, we can make switches, we can make pressure sensors, we can make antenna, simple RF electrodes, data transfer systems, and a variety of simple displays, thermochromic displays, fiber optic displays. That's playing automatically. So I'm going to go backtrack a little bit now and talk about how I got where I am. This is the first work I did at the Media Lab when I got there. I was involved with a project called the Brain Opera, and Turner, when he was talking, didn't talk about what an exciting time that was at the Media Lab. It's hard to remember, and Nuria, you might remember, but like nobody had made anything at the lab at that time. No one had made a physical object at the Media Lab, and it was just a great time. And I was involved with this project called the Brain Opera, and my job was to put sensors in cool-looking things that let people play instruments. And it was a challenge, such a technical challenge, because the sensors would fall apart and there were wires, and I couldn't do what I wanted artistically, and I knew nothing about electronics, and Neil didn't throw me out of the lab. So this is the first, these are the two, this project, the Rhythm Tree, I like to show it because it captured my imagination. I was like, because there are little piezoelectric sensors in there, and it's a drum machine. So you can actually, now it's not going to play. So you can actually, when you hit the sensors, different sensors, because of their shape, trigger different responses in the drum machine. So suddenly there was a non-neutral relationship between form and computation, and it was networked. But the materials that I had to make it were inadequate for me. I couldn't get what I wanted, and I was fussing all the time with the sensors. So the next project I worked on at the Media Lab was sort of a macroscopic material, which is called the triangles. It's an early digital construction kit, which we see a lot of nowadays. And each of these little triangles has a PIC microprocessor in it and magnets on the edges, and then it uses conductive Velcro to help complete the electrical connection. And when they're plugged together, the computer can recognize which triangle is connected to which on which side. And we use that for storytelling. We used it for artistic pieces, and we used it for music pieces. And this was sort of my first interest in, electronic textiles. The conductive Velcro was the first thing where I thought, what kind of materials could I use that were different from traditional electronic materials to do some of the things that they were doing.
Cinderella! Cinderella, where are you? Cinderella! Cinderella! Cinderella, there you are.
So that was a simple storytelling, nonlinear storytelling that we did with the triangles. At the same time at the lab, there was a group called the Wearables, and many people know the Wearables, and it was a really great group. Thad Starner is one of the more recognizable people there. And under Sandy Pentland, they were putting together a fashion show. And they would come to me because I made things. So again, I'll say nobody made anything at the lab, so I was in this great position of knowing how to sew and make things. They'd come to me and they'd say, look at my metal box, and this is my wearable computer. And I'd say, oh my God. I mean, these guys, they come with their metal box and their straps and their big head-mount displays, and there was no hope for them. And I have to be honest that at the time, I was not that interested in trying to wear a computer on my body. I even tried to get one, and I tried to do it, but I was more interested in what it would mean if your clothes could compute, and this was more of a kind of artistic and philosophical idea about it. So this is one of the projects I did for the fashion show. This is the Firefly dress and necklace, and it's a simple, well, it represents thousands of hours of handwork, but it's basically just a simple power and ground plane in the skirt made of conductive fabric with some tulle between it. And then it has LEDs suspended with fuzzy Velcro brushes on the end, conductive Velcro, and when they brush together, the skirt flashes, and then the tassels in the necklace are actually, each tassel sends a different amount of current to multicolored LEDs at the top from this plane here. So they change color as you move and change the tassels. So it was a very simple way to kind of look at materials and how an object might express itself from electricity moving around inside of it. I was also looking at sensing because I was in the music group, and my task was actually to make musical instruments. So this is an early demo of a Roland column keypad. At the time, this was existing flexible circuitry. Obviously, things have gotten better since then. And that's just a layered structure. That's just a layered structure, and it's just sewn, and it's just connected to a pick and then to the computer, and you can use it to play music. Another keypad that I developed at the same time with a series of other students at the lab is this embroidered keypad, which is a capacitive keypad, and each of these numbers represents essentially a low impedance electrode, which is embroidered and connected to a circuit. And I'll show you a little bit more about that technically in a second. This is the keypad. So you can see how the jacket could actually control music. And I have a jacket in my studio, and it doesn't work very well because the speakers are broken over time, but the keypads still work. The connectors to this keypad have broken over time, and I need to go in and to the speakers have broken over time. So the way that this works is that it's basically a capacitive sensing technique. We have fabric electrodes. In this case, we don't have a ground electrode. In later work, I'll show you there's a ground electrode that you have to be in contact with. And you touch the electrode, and the little pin on the pick is actually charged up to the upper TTL level. When you touch it, you pull down the voltage, and the time constant changes so you can tell when you're touching it. So it's a kind of simple digital way to look at capacitive sensing. So I have a little more early work to show, but at this point I thought it would be a good idea just to talk about, why electronic textiles, because this was when they sort of captured my imagination. I'd made these two projects, and I was like, wow, these are really cool. And I've tried to leave them behind at other points in my life, and not successfully. So they get me out of bed in the morning. On a practical level, electronic textiles can achieve a scale, a physical scale that most circuits can't, mostly because they just have more metal in them. But you can make really large circuits with electronic textiles, and partially also because they're highly flexible. Still, electronic textiles is still in its infancy as an academic area and as a business area. So as an academic area, there are very few consistent terms across it, and textiles, which is has different standards of flexibility than electronics. Those two things haven't come together. There are people working on it right now, but it's important to understand that the flexibility of a textile simply exceeds the flexibility even of organic polymers right now. I mean, there's just no comparison, and the reason for it is a conductive yarn basically uses a geometric structure that lets it flex for the same reason that a textile flexes. You have a wrapping that can really bend as opposed to a layered film structure. So you just have a more three-dimensional structure. They're shapeable. You can shape them into different objects, and they have an immediacy in making. I could make these devices, these objects, without having to send them out to be prototyped and things like that, and it was very exciting. Practically, they're a manufacturing process match for soft goods, so textile items are made with textile processes. If you're putting electronics in them, it just makes sense to use the same kind of processes. They're human scale. I spent time in the Silicon Fab Lab. There's something really exciting about working on electronic devices that are human scale and not invisible, that you're bringing that out visibly. They're an integrated material. That means that they allow for the integration of different components into a single material. You can have resistors, you can have conductors, you can have capacitors. So ideally you can use a single material like a chip, and it can actually become the housing of the object, the physical part of the object as well. They have aesthetic advantages, and for me I think those are huge. They're soft, they're intimate, they're beautiful. I think they're transformative for technology. And finally, my artistic motivations are really that I think they're surreal. I mean, what I think they present, they challenge our expectations of technology. I think they're kind of perverse. I mean, I think if technology had been soft, I might have tried to make it hard, you know. And I love the idea of fuzzy conductors. I just think that there's something great about that. They're humorous. This is the electronic tablecloth. This was also done at the Media Lab. And the tablecloth has a RFID tag reader. And these coasters have a little RFID tag in it, and it has also a capacitive keyboard here. And as you can imagine, the tablecloth, I learned everything there is to know about ground making this project. It was really a great project. And this was a game of Jeopardy that we played on it. And it really presented an opportunity for me now to sort of show, whoops, sorry, I don't know if I can go back. To show the visual possibilities of these materials, that they could be something other than standard keypads, that they could become something beautiful. And these are a portion of my thesis, where I actually used the same capacitive sensing technique to do pressure sensing. And designed a series of different instruments whose design reflected the type of music they were trying to play. So this is actually a ball controlling a digital synthesis program, and there's 8 sensors on there that are designed so that they have to be played together in kind of an intuitive fashion. And then this is a ring where you can actually control 8 different voices, and you can do it individually. So you have, instead of an intuitive control, you have a much more one-to-one control over what you're playing. And the music for this, by the way, is by Gilly Weinberg. So I'll start that as my introduction, which is that I'm not a musician. And so I liked making musical instruments, but I felt like I didn't have any control of the output of what I was doing. And so I'm going to take a little aside here and just present a simple taxonomy of interactive objects, which is that if you look at these things, you have if you're making one, you just have some basic stuff you have to deal with. You have processing, software, and interpretation, which is sort of a middle thing. And then you have input, which is sensors. You could see it as software too, but it's basically sensors or wireless data. And then you have output, which is displays, speakers, and lights. So if you're making an interactive object, your options in terms of displays are not great. At that point, my only options were basically like a video rate display if I wanted to do something visual, or a projection. And I wanted something that was more integrated with the object. So when I left the Media Lab, I got really interested in the idea of what I could do with simple, cheap displays, something that was different, and I started IFM. My original idea was to make modules for fashion companies. So I worked with E-Ink to develop a simple 8-pixel display. This is the animated fashion module. It's an 8-pixel display. It's non-emissive. I was really excited about the idea of a non-emissive display, something that changed color instead of lit up. And so this is an example of something kind of beautiful and fashionable that you can make with 8 pixels. It was the first beautiful thing that E-Ink ever made. I can vouch for that. And, and it really inspired me to start thinking about the creative possibilities of simple displays, of positive and negative, foreground and background, of an animation sequence where you don't have control of every pixel, but you've actually physically designed the display. The original proposal was that these things could go into bags and handbags and shoes. And there's actually quite a mismatch in price point and quantity between the fashion industry and designability. And I can, if you have more questions about that, I can go into it. But as it turned out, the tooling cost for one flower was about $10,000 for e-ink, and that just was pretty prohibitive at that point for the fashion industry. And e-ink thought I would sell everyone the same flower. They didn't understand that people would want their own designs. So that it was a really interesting thing that there's just a mismatch in the concept of how design and electronics fabrication could come together. So thinking about simple displays led me to electric plaid, which is a color change fabric, which is it's not addressable. It's a fixed display. It has a certain number of pixels, which basically you can turn on and off, and you can create complexity through design and artistic process, just like you can with a lot of visual things. This is an early example of electric plaid, and this is how it works. It's basically a combination of control electronics, conductive yarns, which are woven in the weft, and then I have more conductive yarns in the warp that provide the contacts. So I have some certain yarns here and certain yarns here. And then I overprint it with a thermochromic ink. And the interaction of the conductive yarn and the thermochromic ink causes areas to change color. And so I've been working, here you can see basically what would happen. You have no stripes on, one stripe on, two stripes on, three stripes on, in kind of a simple demonstration. So the first piece I made with this, I was really thinking about it as a painting, and I put this up because I want people to understand how related this process is to traditional art making as well as to electronics. So the first piece I made was a commission, and I started out approaching it from the point of view of painting. So if you look at the wall here, what you'll see is these are the after colors, the colors that the ink would be after it changed, and then above it are all the swatches for before colors. And I just started designing it like I would a painting. It wasn't really working out for a variety of reasons. I didn't like the squares and the surface of the paint, which led me to really start to look at the interaction between weaving. I was planning to weave it anyway, and between a woven pattern and then an ink on the top. And so here you can see there's a woven pattern which the electric yarns are put into, and then there's a printed unchanged pattern and a printed changed pattern. And then those three things come together. And this was a really complicated piece. I mean, I probably spent 8 months designing this piece. And really trying to play with background and foreground, how different colors would change, where colors could disappear into other colors. And it was a really fun piece to make. So here's the first stage of printing of the piece, and you can see here's an unchanged area, a changed area, and then a more changed area. So thermochromic inks have a time constant, so you don't get an immediate switching, which actually presents a lot of beautiful things. You can have subtle events at the beginning and brighter events at the end, and it also presents a much less controlled environment to act in over time. So this is the final piece. And what was interesting is the person I made it for really loved it, but because it's slow and it takes a long time to return, and I was playing with colors that would change background and foreground, it's hard to tell when it was changing and when it wasn't. So I went to a much more perceptual approach to the fabrics. You know, as I said, so at this point I was sort of like I was using the interactive action of a static woven pattern and dynamic ink and software, and I was using the weave structure to increase perception, and that was really important. I started looking at how black and white and double weave and different traditional weave structures could help increase the perceptual properties of the display. Any display, when you're making it, you have to worry about how it's going to reflect the light, what the white that the black ink sits on, and things like that. And those all just became really important for making this. I started thinking about repeat pattern. If you have a repeat pattern, how can you then violate that so that it becomes meaningful? And then software controlled pattern. So this is half of a 64 pixel piece, and it has a pseudo-random code on it. So, and I'll talk more about the complexity of this, but it has a pseudo-random code on it that actually it enables me to create a pattern in a random manner. So I've linked pixels together across these areas. It's a real challenge to develop software for these things. So it is reflective, so it's going to start here, and you can see in this case the conductive yarns are woven at the top in the black area and they're paired with white, so you get an early event, and here the conductive yarns are woven at the top in the white area. So these are the kind of things you can really get into a level of detail playing with how the weaving interacts with ink and time. You can get into two events where you have an event here and then you have an event here just through the weave structure. That doesn't even happen in software. And you can see that they're paired in a kind of a pseudo-random manner because I consider this is an 8-pixel unit. So you have 1, 2, 3, 4, 5, 6, 7. Well, no, 1, 2, 3, 4, 5, 6, 7, 8. And each of these units has 128 possible patterns that it can hold. So trying to think about what does it mean to have pattern, a software pattern inside of a hardware pattern. And I'm going to talk about that more in a little more detail. Here's a picture of it up close. Here's 3 versions of 64 pixels. So you can imagine how it can become a bigger piece over time.
What kind of power is required for this?
That's a 24-volt power supply, and it's an 8-amp supply. So this is not a wearable system. My commercial, what I'm looking for commercially right now is as room screens and wall covers, things like that. It's not a wearable system.
It'd be good in the winter.
Yes, it would. But you still need big batteries. Nobody wants batteries. People call me and say, yeah, but we don't want any batteries. So I'm going to talk a little bit about sort of the implications for this, for textiles, and how to think about it from the point of view of design. And these are, and what I mean by software primitives and hardware primitives. And I think, so if this is the weaving pattern up at the top, where you have different stripes, and this is something that, and then this is a printed version, unchanged. And as I said, this is an additive process. So you start with orange, and you add green, and you get brown. And then when you turn it on, the green goes away, and you get orange. So this is one thing I didn't explain. This is like a palette I use. This is an electric palette I use when I make my pieces. I just mix the inks, and I test them, and then I turn them on, and they change color, and I can see what they do. So it's a very, hands-on kind of artistic process making these things. If you took that textile and you divided it into 4 primitives, this is how textile designers work with repeat. So, and then these are the before primitives, and these are the after colors, right, in the ideal state. And each primitive has 8 pixels, right? So here are the textile primitives before and after. Now, there are 256 possible primitives for each one of these things. And that's what I call a software primitive. So you have a hardware primitive that's fixed, but there are 256 software primitives within each hardware primitive. And if we just take 5 for those 4 units, 5 simple software primitives, and we start to make fabrics. So here's a simple design before and after. This is just 8 of the software variations you can create in a single fabric. So the implications for this are that a single piece of fabric can potentially hold dozens of combinations and designs. So and this doesn't include time, which is another factor which is very complicated in working with these kinds of novel materials. So I think of this stuff as really an alternative to video rate media. I took it to a show in Europe last year I was surprised. It was so loud. The show was just like, all there was sound art and light art. And I was really surprised. Just the people from the city responded really well to something that was different than loud, bright art. And it took them a little while to look at it and experience it. But once they did, they spent a lot of time with the piece. And they responded really well. So I think that the idea is that it's an alternative to what we have out there right now. And I think you could look at the fact that the thermochromic ink has this time constant as a disadvantage, or you could just look at it as like any material that an artist has to work with. There's always properties of that material that you have to come to understand and know. And I think that as artists work with more and more physical electronic materials, I mean, even with ink or whatever, those materials are going to be something that they need to understand the way that they learned to understand wood as in the arts and crafts tradition at the turn of the century. People do expect speed from technology, so it takes a little while for them to focus on this. And also the fact that it's non-emissive is really confusing. People expect that peripheral light, that ambient light, to come out of something, to flicker in the room, to get their attention. So that takes a little bit of a challenge too. But it also presents possibilities like a camouflage clock. So now you could imagine a textile clock. So things that textiles couldn't do before, now they could become a clock and tell time. They can convey information, simple information as well. These are designs for a large installation in England. And so I'll just wrap up this end of the talk and then show you a couple of the things that I'm doing with sensors and more commercial things at commercialization at IFM. So these are my pom-pom light switches, which are an extension of the capacitive sensing work that I did at MIT. So they're dimmers, they're wall dimmers. You install them in the wall. They turn on and off. And they're the first product. They're actually under UL Lit testing right now, which is really exciting. And they'll be the first electronic textile product to be UL listed. And they're the first of a product line of lamps and other sensors for other devices, and then what will be color change room screens and things like that. And that's an interior design focused product line. Here's a range of design possibilities. One of my particular favorites is the sensor shag, which I think is a really fun idea. And right now I'm also finishing up development of a fiber optic, a simple single to 4 pixel fiber optic display that will be embroiderable. It's called IFM's Info Patch, and the idea is that it can be paired with some of these new wireless personal data systems like spot or ambient devices, and it can change color to tell you the weather. So if it's cold, it'll be blue, and if it's warm, it'll be red. If it's raining, it'll be flashing. Electric plaid is not right for the fashion market for a variety of reasons, so I've been working to figure out a display that you could actually make with textile processes, could be incorporated to different products, and get some simple information into technologies. This is the weather coat. Some handbag designs, development work that we did for a fashion company. How fast are you running? So shoes with simple displays to give you performance information. These are the kind of concerns of fashion companies that are looking at this information. So I'll just conclude with some of my artistic motivations. Basically, I'm really excited by the idea of fuzzy conductors, and I think for me, it's like putting a toilet on the wall in the electronics world. It's like, it's like saying, look, you guys, this could be something else. I'm also really excited with beauty. I think beauty has a lot of meaning in people's lives, and it's been underrated in the art community. And that's something that I see as very important to my work. I like the surrealistic and perverse aspect of these materials, the fact that they're transformative. And they let me explore something which I call the metaphysics of electricity, which is the idea that a material can have all this power inside of it, whether it's a chip or a textile, and I can explore it in a physical way. And I feel like if you know the work of people like Joseph Beuys or artists who work with materials as having meaning, that the idea that there's electrical meaning and power in these materials and that they interact with computation is for me really exciting. And I think one of the great things that's happening right now is that computation and art making are really fusing. I mean, there's so much excitement around how computation and art can come together, and not just from the point of view of Java applets, which is one really exciting aspect of it. And I think that computation and physical computing materials are opening up unknown areas for future art. I mean, they're really challenging the Academy of Art right now and asking people to ask fundamental, formal questions that artists haven't been able to ask in, 100 years, because a lot of those problems were solved. And so from an artistic and technological point of view, I think that that's just an extremely challenging time and a wonderful time for artists working with computation and new materials.
How well can you control the impedance of wires in fabrics? Like if you were making an antenna or your resistive wires or
Right.
so forth.
They're never going to imitate copper. There are some, so it depends on if you're looking at like impedance for like DC circuits or if you're looking at high frequency impedance. For high frequency impedance, the stitch pattern and the weaving pattern becomes very important because the way that the things come together, the electrons get caught in the edges of stuff. You really want a smooth surface, and yarns tend to be hairy and fuzzy and have geometries to them that you really have to control very carefully for high frequency systems. For DC systems, you can do pretty well. You're not going to imitate a wire per se, but you're not at any disadvantage necessarily from trying to create a long wire. Do you see what I mean? Like if you want to imitate, if you want to make a serial bus and you want to do a USB standard, you're going to have trouble and you're not going to have a textile-like feeling. But if you're willing to have not meet the USB standard but still pass USB data, you can get away with it. You just don't want to, you have to be careful not to create resistive ladders and other structures like that. And various yarns do different things. So if you want a yarn that you can weave, certain yarns are good for that. If you want a yarn that you can sew, certain yarns are good for that. And their impedance is related to their sewability just because of the amount of metal that's in them and their geometric configuration. Does that answer your question?
What's your current draw on the panel, and how warm is the fabric?
The fabric heats up, the current draw is 8 amps on not for this one, this one's 4. It'll draw 8 amps for 64 pixels. It draws about a half an amp per pixel, and the fabric heats up to just above body temperature. So that's where the inks happen to be, but it's a good place because if it's lower than that, then they just get set off by the environment. If it's higher than that, it's too much current.
When I look at textiles and you got warp and width, and look at VLSI where I've got polysilicon and metal and other stuff, it all looks alike, and it's really a seductive analogy, but it doesn't work.
Yeah.
And, as in the old days when I would finish a chip design, I would hang the check plot up on the wall, and that was my version of art.
Yeah.
This art doesn't do the circuit I want to do. So there's this disconnect between the functionality and the aesthetics, and I'm just curious how you bridge that.
That's where the capital investment comes in. There's two challenges. One, we don't have the yarns that we need, and part of the problem. Okay, so within the textile itself, we don't have the yarns that we need, and part of the problem there is that people are still approaching electronic textiles from a film-based structure making. So you look at people that are making batteries that are supposedly for textiles or fiber batteries. Okay, they might have a radius of curvature, something like this, and they're like layers of, silicon and materials that you just bend them and you crack. If you look at a textile structure, you have multiple things that are twisted together. You have redundancy, you have ability to bend in the geometry of the wrapping. Sigurd Wagner at Princeton is doing really good work trying to combine the idea of nanotechnology and microtechnology with textile flexibility and structures, but there's not a lot of that going on. The other problem is connecting to them. So even if you have the yarn, how do you make a connection to it, which is a big problem, and interconnections. There's just no standards in the industry. There's even very few standards for people who work together to talk together. Like if you go and run patent searches, there's no standard way to refer to things. So you could be searching for something where there are a dozen patents in the area, but you just can't find them. And then the other challenge is that, so textiles, and this is why nonwovens present the future for electronic textiles, because nonwovens provide an ability to create a computer-controlled, isolated circuit environment. And wovens, something like electric plaid, is really determined by the warp and weft. So if you go out and you buy a fabric, like when I went to Muharrem with this, like, we like this, but we have to have a third partner because we have to have a place to put it because it's a certain size, right? So there are fabrics out there that are a certain size, and you can't just cut them. It's a circuit. If I went up to your circuit and I cut it, it wouldn't work. But everybody who works with a fabric expects to cut their fabric to shape that they want. So the trick is, how can you get a circuit-based, CAD-controlled approach into a textile? And nonwovens and some of these newer processes for, I think, really present a possibility. We're really at the same time, like when you just had big transistors that were television to, your transistors were this size. We don't have an integrated circuit process for this area.
So I'm coming back to sort of this idea of the impedance of stuff.
Okay.
If I have like a 1-inch Velcro square,
right?
What's the impedance that I would get across? I mean, I imagine a battery pack, and a military guy taking a Velcro thing and clipping a new one on.
Top to bottom.
Yeah.
You probably get
across.
Across.
I mean,
if you Velcro them like this.
If you got two Velcro things together, so.
If it's really together, you probably would get. I'm going to have to go from memory here, but 30 to 100 ohms. Okay. If you measure across, you might get a little bit more. But you can improve that by improving the Velcro, by putting things that help connect it better top to bottom. Conductive Velcro is made for shielding. So a lot of these materials were originally made for shielding, and now they're developing better materials. But for instance, something like Aerocon, which is a silver-plated fiberglass yarn, it's been around for about 5 or 6 years from DuPont, and they haven't found a commercial application for it just because of cost. It has a very, very, the single-grade yarn has close to 0 ohms. Not 0 ohms, not copper, but close to it. But you can't. It doesn't have the. It's so costly that it's hard for people to find a commercial application for it. And then another problem is just building shielding structures. Like, how do you insulate between things? And it's a lot of very, very difficult questions, and a lot of ways to do it, especially if you're a surgeon. But the question is how to do it on a larger scale.
What do you see as sort of like the biggest first commercial application?
The pom-pomlets. I think if somebody can get the body sensing stuff right, it's a great commercial application. But it's hard. There's been a few companies doing it, and they're not really. They're sort of only kind of around now. People don't answer the phone anymore, so. It's hard. I think one of the things that I find about electronic textiles is people think they're magic. I was talking to a radiologist, and they're like, I want a coat that changes color to tell me if people will respond well to chemotherapy. And I said, well, how do you know now if people are going to respond well to chemotherapy? And he was like, we don't. What methods do you use now to make that, how do you instrument that? And they're like, we don't have a way. So that's where the challenges come in. So.
What about antennas? Do you think that's
That's a good point. I think antennas are very possible. There's a lot of development in that area. One of the things that came out recently was a hat that shields your head from cell phone stuff. So I think there's a lot of possibilities in that area.
So beyond capacitive and pressure sensors, what other kinds of sensing options do we have?
Well, there's a couple companies that make a sort of a foam-based and fabric-based, foam and fabric-based switching tech systems. That some of them have like a resistive material, and when you put pressure, they put contact through it.
That group that did the foam?
Well, I don't know if they did the foam. Electrosen and Sensitech And there's the commercialization challenges for them still lie in the lack of standards.
So is that the
And-
case when you capacitive or independent?
Well, both in those cases. But they're basically row and column structures, simple row and column structures. So they have, they have some issues with, crosstalk and things like that. But
The thermochromic ink, the fact that you use the word thermo in it infers that there's dissipation, changes color. Are there any alternatives that don't dissipate?
I mean, they don't have to heat up.
Don't have to heat up.
The problem is you got to have a top electrode. And what textiles do well is build structures this way, not this way. And that top electrode is just a bear, and so like Elisco did a really great project where she put silkscreen electroluminescent ink directly on, a bottom electrode and then put the indium tin oxide on the top and connected to it. And it was really beautiful, but connecting to it, keeping it alive, it's 150 volts, keep it from shocking everybody. It was so that top electrode, it's just, and even in e-ink, that e-ink thing that I had, it's not flexible really. You bend it, it fails over time. It's just it's just an issue for textiles because the structure of the textile is so lumpy that there's just no way you can get that precision of distance between the bottom and the top electrode. It's just that level of precision in distance is not possible. So this fabric takes advantage of the fact that we can build things this way in textiles really well, and that the distances aren't that precise. I've definitely thought about electrochromic materials, and there's some people doing stuff with yarns, but there's still a ways away to go before that will happen.
I have to admit, Maggie, I don't think we've ever had an artist come here and discuss impedance matching before.
Oh, good.